Welcome back to my series on the 2023 Advent of Code. We're up to day 3. I'm Elliot, I build stuff, and let's jump straight in on this one. So day 3 had us looking at a problem that they called engine schematics. I think the name of the day was gear ratios, which will become apparent in part 2. And our input file looked like this. It was a series of lines with numbers, full stops, which represented empty space, or symbols. So these asterisks, hash, plus sign, dollar sign here. Part 1 was all about finding what they called part numbers. And according to the rules of the puzzle, anything that was adjacent to a symbol was considered a part number. So in this case, 4, 6, 7, and 35, they're both adjacent to the star here. This one diagonally and this one up, down. But 114 in this example is not touching any symbols, so it's not counted as a part number. First thing we had to do is find all the part numbers, sum them together, and then spoilers for you. If you haven't done this one already, the total of those is 533,775. But let's have a look at the code really quickly. Before we dive into the details, I introduced 2 structures within this problem. There's the coordinate structure, which has a U size for the row and the column. That's used to reference a point on that schematic grid. We'll see why that's useful in a minute. Then we have a part number. A part number starts at a coordinate and ends at a coordinate. So that's the location of the first and last digit in that part number. And then it has the value, which is that number itself passed as an unsigned 32-bit integer. So what we do here, as with many of the problems, the first thing we do is read day 3 into a string to start processing. In this problem, part 1 specifically, just ignore this gears variable. We'll come back to that one for sure. But we have 2 data structures here. We have a hash map, which is the parts variable, and we have a hash set, which is the symbols variable. Now, technically speaking, you could do just part 1 using a hash set for parts, but we implemented part 1 and part 2 here, and we'll come back to show why that's different. But hash sets, for anyone unfamiliar, it's a way to have a collection of a certain data type, in this case, the coordinate structure that we had before, and it very quickly can tell you, do we have this coordinate in our set or not, by computing the hash of that structure. Hash map, quite similar, except at the location represented by the hash of coordinate, it stores another data structure, in this case, a part number. As I said, gears, you can ignore it for now, but that's another hash set. So first thing we do is parse the input file. We store a placeholder for a digit. If we're reading the digit in one number at a time, we just keep this as a place to store the digit that we've read in so far. We store a placeholder for the start location of that digit, if we're parsing a digit. And then we start moving through row by row, column by column. We use the enumerate function here to give us both the value of the line or the current character, as well as an index, which we'll see is helpful a little bit down the line. So first thing we do is we check, is the current character an ASCII digit? So 0, 1, 2, all the way up to 9, they're ASCII digits. If it is, one of 2 things can happen. We can either be finding the first ASCII digit, and that will be when our digit placeholder is empty, in which case we need to take note of the start location. And if we're not, or even if we are, we continue then to multiply the digit placeholder by 10, and then parse the current character to a base 10 number and add it to the current digit. So in that example before, we had 4, 6, 7. So let's imagine us working through this one. We'll start with 0 in the digit placeholder. We'll find a 4. So we'll do 0 times 10 plus 4, which is 4. We'll move on. We'll find a 6. We times it by 10, so 40, and then add 6, which is 46. And then we find a 7, so times it by 10 once again to get 460, and then we add the 7 into the mix. And then if we don't find a digit, so let's say now we're on to that full stop right after the 467. If we had previously been tracking a digit, we say, okay, we've reached the end of a part number. Notably, parts can't span beyond the end of a line, so they don't wrap around. You'll see there's a very similar check to this one at the end of the inner for loop around the columns. But we get the part number, we store that start location that we found representing the start of where the digit was, and then we put that into our parts hash map. The key is the start location, and then the part number structure itself stores the start location where we're up to -1 column, because we've found sort of the first character beyond the end of the digit, and then the value itself. And then we reset the value back to 0. After that, we check what it is that we found. If it's a full stop, nothing more to do. That's just an empty space. So we continue. For part 2, if we find a star, we put it into the gears hash set, which we talked about before, but we will come back to that. And in either case, we store the coordinate of the symbol into the hash set called symbols. So any of those $signs, pluses, hashes, and the stars, they'll all live in that hash set. As I mentioned before, there's also a check here at the end of the column for those part numbers that butt up right against the end of the row to say, hey, we've reached the end of the column. If we were looking for a digit, it's by default over. So put that one into our parts hash map and then reset, ready to check another line. So after we're done with this, we have a look at the data that we've collected. So we store a running total for the part IDs. For part 2, we saw some gears related stuff, but again, just skip that one. And then we start to loop through all of the values in our parts hash map. Now, when this was a hash set, this was exactly the same, which may leave you thinking, why do we need the keys to be coordinates? And you'll see again, that's for part 2. So we loop through all the parts that we found, or the part numbers, I should say, and we do a couple of checks on them. So I'll just bring some of this more into view. So we've got a variable here called skip, which we use to break out of some of our inner loops, which you'll see in a minute. But first thing we do is we look for the minimum row. So what we're going to do here is, let's jump back to the example. We find the digit itself. Let's use, say, 35 as an example, somewhere nicely in the middle here. And what we're going to do is we're going to check all of the spaces surrounding that number and look up in our hash set to say, hey, was there a symbol in any of these empty slots? If there was, then that counts as a part number. And if there's none and we get all the way around, checking all the surrounding squares, then we know we can safely ignore this number in our part number total. So part of this check is that, hey, if we're in the top row, use 0 as the row to look across. Otherwise, use the current row from the start position -1, so 1 row above. Max row, use the end row +1. Technically, that can go beyond the bottom of the schematic, but because we're storing the coordinates, it doesn't matter. There'll just never be anything there. And then we loop through a variable row, which iterates through the values row min to row max. So let's say we're back on that 35 example. This is row 0, 1, 2. So it'll go between 1 and 3. And then you'll see we do something very similar with the columns. So we look to the left and then we look to the right and we iterate through column left to right. We then do a lookup into our symbols hash set. We say, hey, is this coordinate in there? If it is in there, then just ignoring this for a second and jumping down here, we add the part number to the running part number total. And then we store this variable skip, which just says, hey, we found a match, you can just bail now. And we break out of the loop. Otherwise, we continue to search in all the surrounding squares. If it's next to 2 part numbers, it doesn't count any more or any less than if it's related to just one. So we can safely bail from here and keep the part number total ticking along. We'll come back to gears in a minute, but then we print out the part ID count, which is the total of the part numbers. And that's it for part one. So fairly straightforward. We just loop through, we do a bit of a surrounding area check, and we then report that total. Now having a look at part two, the difference here is that these asterisk symbols are not just any old symbol anymore. They're treated as a special type of symbol called a gear, and they're adjacent to exactly two part numbers. Sorry, they're a gear if they are adjacent to exactly two part numbers. And we need to calculate this number that they call the gear ratio, which is the result of multiplying those two numbers together. So looking back at this little mini schematic that they gave us, this one here, this first asterisk is a gear. It's adjacent to 467 and 35. If we multiply those two together, it's 16345. And then there's another gear down here, which is adjacent to 775 and 589, I believe. And that equals 45149. And then they note here that 617, that's not a gear because there isn't a second part number for it to be adjacent to. So those are the new rules. We got to go back through and we need to parse, or we need to find all the gears, and we need to do these checks to say, are they adjacent to two part numbers? And if they are, then we need to calculate the gear ratios. So let's have a look. So right back up near the top of this function, we have this gears hash set that we talked about before. That stores the location of any gears that we find. So if we come back down here into our parsing section, you'll see we've got a special if statement here for is it a gear? And there we just store the coordinate. Coming down into the second part of this problem, we have some extra work going on if we have gears. Now we store a running total for the gear, that's nothing too crazy. And we also store a hash map that maps a coordinate to a vector of part numbers. So what this does is it stores a reference to the part numbers that are adjacent to this particular gear. And then after we've done that, we can then check if there's two, and if there are, it's a gear. The reason we did it this way is that we get to reuse a bunch of the code that we wrote for part one. So this parsing loop all still gets reused. So we saw this before, we loop through. Well, let's look at the gear specific code. Next thing we do is before we have a look at the parts, we say, alrighty, is there a gear at this position? So there may be a symbol, and if there is that symbol a gear? If we've never seen a gear at this position before, we just insert an empty vector to store our part number references in. Otherwise, we grab that vector and we push the part number to the end of it. And then we do the rest of our checks for part one. After we've done that parsing, we then come down to go through that gear parts hash map that we created above. So for every gear that we found an adjacent part number to, we loop through it and we check how many part numbers it had in its list of adjacent part numbers. If that happens to be exactly 2, as were the rules of this puzzle, we grab the first and the second part number from that vector, multiply them together, and that becomes our gear sum. And then we report that number at the end. And if you did all of that correctly, we got 482,36071 as the answer for part 2. So again, day 3, pretty straightforward. A little bit of an introduction to various data structures there, certainly with the hash maps and the reverse mapping and things like that, but nothing too out of the ordinary at this stage of the set of puzzles. So hopefully you found that useful. If you did, please consider a like or a subscription, and I'll keep making these videos. But until next time, I'm Elliot. I build stuff and I'll catch you later on.